Thank you very much to the organisers for putting me last. That means it's quite early here. I think it's the earliest I've started watching talks in a while, at 7 a.m. here. And I think it's a good idea to put me last because my talk will be a bit lighter on the maths. Always happy to answer any details about the mathematics, but I haven't put that much in the talk. So I'm Art. I work here at the University of Sheffield in an engineering department, but I'm not really an engineer, which is how I came across the subject of the talk. So I consider myself an applied mathematician, and that's me doing maths on a board. So it took me a while to sort of adapt to an engineering department and sort of see all the interesting problems they were doing. And but being in an engineering department, I did get in contact with a lot of new problems really that are definitely useful. So in this one, first I'm going to convince you that we have a lot of steel around us in our world and infrastructure. There are some steel bridges. And all these structures are designed to hold compression and stress in a certain way so that they are more stable, don't damage due to fluctuations in heat and wind. So, for example, in this bridge between this two cliffs is designed to have compressive stress along the arch for stability. And so it's important for us to know over time if that compressional stress changes, because it would really seriously affect the structure. Here's an example of a rail that's buckled because of compressional stress along the rail axis. It's not supposed to look like that. A stress builds up along the axis, and then if a train goes over it, or if you have an earthquake or anything, it'll just buckle, and that's really terribly damaging. Here's another example of a stress-induced fracture. So what I'm trying to convince you here is obviously that is almost an obvious thing, is that stresses within solids are very important to monitor over time and to measure. The current ways that stresses are measured as sort of considered gold standard, I would say, are not that sophisticated really. Here's a little machine, it's almost like a little gremlin that punches holes in the structure. So it quickly punches a hole, waits for a while, observes how the hole will change, and estimates the stress based on how the hole changed shape. You can imagine punching holes all over your structure it isn't really ideal. Not to mention that it's not easy to quickly move this thing around the whole structure and you'd have to, everywhere you estimated, you're punching a hole, so you've got to choose very carefully where you want to estimate your stress. So this brings me to using ultrasonic measurements, which is why I'm doing this in a WAVES conference. So ultrasonic measurements have a lot of advantages. They're non-destructive, they're quick to measure, they have a lot of information. When you measure them and they come through to the other side, you can change the frequency, you've got the speed of the wave, you've got the amplitude, there's a lot of information there. Disadvantage is that you need quite sensitive equipment to pick up the signals, and for engineers, interpreting such signals is far more complicated. There's been a well-known example of a type of ultrasonic measurement that can give you the stress. It's called birefringence, and there's an equivalence in optics and other wave areas. But basically, if you have two different polarized shear waves, so can you see my mouse? I'm going to guess you can. If you polarize one of the shear waves in the x1, x3 plane, and you polarize the other shear wave in the x3, x2 plane, and you send them across this, say, bar of steel I've got here that's under a in-plane stress, the difference of their speed square will give you access to the stress. The only issue there is that there's this constant K that depends on the material. So when this was first brought over to ultrasonic measurements, I think maybe 60 or more years ago, it was considered that this would be the way forward to measure stress. But that has not happened. It has not turned into a device that's been used by industry. It's never been, the success has never come. And one of the reasons is that this constant K varies quite a lot. Even if you take a piece of steel in the lab and measure it, even if it's the same type of steel, the constant K can change as much as by 50%. So the issue is, how do you measure K, capital K? And it's actually very difficult to measure capital K with a simple ultrasonic setup. So the issue with this way of measuring the stress, and in fact, in all the ways of measuring stress as ultrasonic measurements, is that you need prior knowledge on the material constants, which you might require up to 6 constants for weakly nonlinear solids. So if you are aware of weakly third-order elastic materials, you have these extra 3 elastic constants that are quite difficult to measure and know, and they are the extra constants which couple any waves to stress. So my idea was to look for ways of measuring stress that didn't require these constants. Because there's been, well, basically because there's been about 40 years of effort in trying to measure these constants accurately and use these well-known identities. So my idea was, well, people have tried that, let's try something different. Let's try to devise a measurement that you don't need the constants. So as any good solid mechanician does, you go back to the nonlinear field theories of mechanics by Noel and Truesdale, which is a really tough read, but there's a lot of information in there. And I'm looking, and the term I'm looking for is universal relations, they're called, between the velocities, is this velocities? Yes, between the velocities of the wave and the stress tensor. Right, so a little bit about nonlinear solids and coupling waves. So the way that we usually model this is that we consider there's some configuration with some stress, sigma, and that when you superimpose a small elastic wave on an ultrasonic wave, you take it to a new configuration that has a new stress. So you've added a little bit of stress, delta sigma, because of the wave itself. And some people call them stress waves. So the simplest case to consider is statics, no waves at all. Are there any well-known universal relationships between the strain and the stress? And there are things like, for isotropy, you have coaxiality. You can change the order of the stress and the strain tensor. And you have a nice little one about simple shear, which I think I'll illustrate in a little bit more detail, just to show how interesting these universal relationships can be. So here we've got, if you're familiar with stress tensors, sigma 1, 2 is the shearing stress on the top face here and also on the bottom face. And sigma 1, 1 and sigma 2, 2 are stresses sort of are considered, if you had a face that's flat, it's how much is being pulled this way, sigma 1, 1, and sigma 2, 2 is how much the top face is being pulled up. So the universal relationship says that the total amount of shearing, this displacement S, is always equal to this relationship with the stress. So you could think about designing a way of measuring the stress by shearing solids. Of course, that doesn't work. That works great for soft solids, not so good for a piece of steel, but still an interesting relation. And so can ask the question, does there exist other universal relationships for statics? So usually the way in most of the literature you describe how a small added bit of stress relates to the strain, the elastic strain you've created, is through some fourfold tensor that then depends on the stress itself. This turns out to be quite difficult to design, to spot universal relationships and to design new measurements, because this is a very horrific fourfold tensor. A nicer way to write this is in matrix form, and by using a bit of tensor algebra, we can reduce it to this. Something like this. So you've got that the small added stress from the wave is something that's related to the strain plus the stress of the reference. And these alphas are, in a sense, material constants, but they're actually functions of sigma. Right, so going back to statics, I won't go over the details, but if you simply write out what is the incremental stress, and you ask yourself what kind of identities you could get by having different combinations of the strain contracted with this stress equal to 0. So you're looking for identities which depend only on the stress and the strain. You can prove that there exists only 3. There are only 3 for linearized strain for statics. So if you can do it for statics, maybe we can do it for dynamics, for waves. The extra difficulty being here, of course, is that in dynamics, rather than satisfying just the divergence of the stress equals 0, you've got this, the double dot in time of the strain. Well, it's actually not strain, isn't it? It should be U here. Small mistake. Oops. U being the displacement, which is shown up here. Yeah, so not the strain, it's U. Right, so let's turn to dynamics and think about finding universal relations for dynamics. So you've got conservation of momentum to satisfy. Let's keep things simple. Let's consider only bulk waves, because there isn't any proof to show all universal identities, relations in dynamics. So rather than trying to prove everything, let's think of bulk waves. So here's a little illustration of what this V is, which is the velocity, because I'm going to be using this in later slides. So if you've got some basis En this way, some basis Em that way, the wave that corresponds to the velocity Vnm travels in the N direction and is polarized in the M direction. It's a shear wave. And if it was Vnn, it would be a longitudinal wave because it would be polarized in the same direction it travels. Let's consider that we've diagonalized the stress tensor to make things simple as well. And now let's look for relations between stress and the speed. So why only the speed and not the amplitude? So this might not be immediately obvious because a wave has amplitude and speeds. But in ultrasonics, it's far easier to measure the speed of a wave than it is to accurately measure its amplitude. So that's something just from practical experience. Measuring the amplitude requires a lot more sophisticated equipment. So there isn't any well-known universal identities except one notable exception. And that is that if you take a shear wave polarized, two shear waves that are sort of polarized in the same plane, but one is traveling along En and the other one is traveling along Em, their difference squared gives you access to the stress directly. No material constants. It's okay to have the density because that's easy to estimate. And this also leads to this strange identity here, which I'm not sure what the use is of that. So great. Got a universal relationship, the golden goose from 1966. It was hidden away in the nonlinear field theories of Knoll and Truesdale. So all you had to do was open it up and read. You send one wave across the sample of steel, like so, polarized in the same plane, and then you've just got to send another wave that's inside the material along the steel somehow. I'm not sure how that's going to work, and that's when you realize that it's impossible to send such waves easily. How can you generate a bulk wave inside this bar, traveling along the bar itself? Obviously, you can create waveguide modes and all sorts, but they're not the same as the bulk wave mode. And so I asked my experimentalists if they could do that, and they were very disappointed in me. So I changed direction and instead of looking for universal relationships, I've considered that doesn't exist in a simple way to create a measurement. What about non-universal relationships? That means, how about specializing to a class of materials that we're interested in? So in steel, solids are weakly nonlinear. They're basically third-order elastic solids that depend on those extra three constants. So wherever you see the stress multiplied with the stress itself, you can just cut that out. It's an asymptotic expansion for weak stress, or an asymptotic expansion if you think about hyperelasticity for third-order strain. So, okay, we're looking for non-universal relationships, specializing the material. Now, what other kind of measurements we could possibly take? It's easy enough to build a wedge to send a shear wave or a pressure wave at an angle. So I'm going to consider only shear waves here. So I'm going to call the velocity of this shear wave polarized in this plane, traveling at an angle θ1, v θ1. So you specialize all you can. You list all the types of measurements you can do. Remember v θ1. Now we're going to ask ourselves, when is the difference squared of these two shear waves independent of the material constants? Well, why is this even a good question to ask? The reason it's a good question to ask is because we know that it's universally true that when the angles of the shear waves are different by 90 degrees, i.e. they're traveling in 90 degrees, the direction of travel is 90 degrees different, then there is a universal relationship that says that they're different squared gives you the stress. That's from the book of Noel and Truesdale, a well-known identity. So it's reasonable to assume that if we weaken the assumption of asking that this be true in general and ask that it's only true for third-order elastic materials, perhaps we can expand these dots. And that is exactly what we was able to do. Turns out that the dots turn into full lines when you specialize to weakly nonlinear solids. So if you take any 2 points on these lines and take their velocities, the difference squared will give you the stress. There is a small adjustment here. So this is how I discovered this, what I've called the shear wave stress identity. The difference between two wave speed squared when their angles are plus or minus 90 degrees can give you access to the stress, but you've got to divide by the cosines. You've got to know the angle you've centered. So this is what it would look like roughly. You build two wedges, send two shear waves polarized like so across it. You measure it on the other side, and voila, you've got access to the stress. So I was very excited. I went back to the experiments, ran across the corridors, and that's when COVID hit. Well, it was actually, we were in COVID already a long time by then, and there was no entry, social distancing. So we turned to finite element simulations to check that we would be able to measure these in a reasonable, if they're sensitive enough to the measurements. Obviously, we know it's true because the math says it's true. You can just do a synthotic analysis, but it's good, especially for engineers, to do finite element simulations to convince how sensitive these measurements could be. And so we did these in COMSOL. Guiyang Li is an expert at these. And here we have some of the results where you change the angle, we can see the change in wave speeds and the identified stress. But if the best plot here is on the bottom left, we can see the applied stress versus the identified stress. And below it's megapascals. Rail is one of our main applications, so we don't need to go really beyond, nowhere beyond 800 megapascals. This is all way too high already. And the errors are, very low. We would be we'd probably be happy with 10% error. So I went to submit this into journals of non-destructive testing. They were very supportive. The Structural Health Monitoring Journal said the authors should conduct some real experiments and didn't send it out to review. The chief editor of the non-destructive E International said any submitted manuscript must contain extensive experimental work to support theory. Said please don't resubmit. Although I would like to say that both journals clearly said that they do publish papers that use numerics and theory only, but the current chief editors do not agree. Then an unnamed theoretical journal said didn't send it out to review as well, said they think this should be submitted to a journal that specializes in non-destructive testing, such as the Structural Health Monitoring Journal and NDE and E International. So that sort of led me into a loop. So eventually we submitted it to JASA, the Journal of Acoustical Society America, and it was sent to review with very positive reviews. I just thought that was a nice story to tell. And there it is. Since then, we've now got a range of experiments on the go, trying to both check this experimental sensitivity and deploy this to rail. And yikes, doing experiments is complicated. I'm glad I'm not the one who has to do all the details. But in Sheffield, they're experts in ultrasonics and steel. So if you have any use case for using ultrasonics and steel, please feel free to contact me. So summarizing the story, start with your favorite unit. You want to find new measurements. It doesn't need to be just of stress. You can find an idealized identity that relates the two things you want. In this case, I want stress and sound speed. You can specialize to your class of material if you're working in solid mechanics. In my case, it was weakly nonlinear solids or third order solids. You can parameterize all your measurements, and you put it all together in a mixing pot. You can discover your own new universal, your own new identities for measurements, and that is the recipe. So thank you for listening. It's light on the maths, but I'm happy to answer any questions about the maths. if there are any questions.
Okay, thank you, Art. Are there any questions? If not, I'll just make one comment.